Hi, I'm Tucker. We're going to spend a little bit of time now looking at machine learning. It's a preview for stuff that we'll cover in later sessions. So I hope you like this little sneak peek at what machine learning is about. Okay, well, let's start with the definition. Let's think about the problem. Let's think about the problem of all this data in the market. So there's at least 13,000 securities trading in North America. If you had, there's perhaps dozens or hundreds of information sources you could use. If you use fundamental and technical factors, on the order of 120, you could potentially use 250 trading days a year. That means in just 5 years you've got nearly 2 billion data points. How can you sift through those in the sense of backtesting or forward testing to figure out what you ought to do? Well, this is something that machine learning can help with. What's machine learning? So, quoting from Wikipedia, machine learning is the construction and study of systems that can learn from data. And as you know, we've got lots of data in the stock market. Machine learning can be used for classification. In other words, think about face recognition. You show a machine learning system someone's face. Can it recognize it? Can it classify that face? In the case of stocks, it can identify, perhaps, classification could be used to identify, is it a buy or a sell. Another use of machine learning is regression, which is basically a form of numerical prediction. And that's when I use machine learning, that's primarily what I use it for with regard to the stock market, is to forecast price. So here's a big picture how it works. I apologize for my slightly rough hand drawing. The goal is to create a model, and all a model is something that takes input, transforms it into some sort of output or prediction. So we represent the input here as X and the output as Y. X might be some condition of the stock or a description of the important factors, Y being a forecast of a future price. We use lots and lots of data to build up these models, run that data through a machine learning algorithm, and that's where we get our model from. So this is just looking at that in a little more detail. X is the observation, Y is the prediction. Now here's a real simple example. I made this data up, so don't go looking up on the web and discovering that my sort of data here is wrong. That I understand that it is made up, so bear with me. But I thought it was a decent example. So we know that change in barometric pressure affects whether it's going to rain. So here's a little chart of data, again made up data, where we have along the x-axis there different changes in barometric pressure. So if the barometric pressure goes up a lot over to the right, that means we're not very likely at all to see rain. And the vertical axis here is how much rain we get. If barometric pressure goes down, we're much more likely to see rain. And so each dot there represents 1 day's observation, where the X position represents what the change in barometric pressure was, and the Y represents how much did it rain that day. And I've colored the instances where it rained with green dots and where it didn't rain with red dots. Now, we can model this. Let's think about what a model might look like. Here's an example of a linear model. It's represented by that blue line there, and it's a simple model which says Y, in other words our predicted amount of rain, is equal to mx plus b. So remember, x is what's the barometric pressure, and b is essentially where that how high up or down that line is. Now, one thing to mention here, just as an aside, the CAP-M is also a linear model that relates expected returns in a linear way. So y is an expected return, m is beta, x is how much did the market change, and b is actually our alpha. So just to draw a little bit of an analogy there, CAP-M is a linear model. Anyways, here's a linear model for this rain problem, and it models it okay, but notice over here it doesn't predict how as much rain is going to happen, and perhaps here it predicts that there'll be more rain than typically occurs. Well, we can, and this is a kind of this is a group of models called parametric models, and what we're learning is the parameters, and we can learn these parameters. In fact, a lot of people wouldn't even consider it learning. We can just apply linear regression to the well-known algorithm to these points, and we can get this M parameter and this B parameter. So that's learning a model. Now we can learn more complex parametric models. Here's an example of a polynomial, and it fits the data a little bit better, doesn't it? This is a second-order polynomial, and so we have to learn more parameters. We have to learn this this coefficient, that coefficient, plus the b. We have to discover 3 parameters. Now we could add even more degrees. We could learn what is we could learn up to x cubed, x to the 4th, and so on. Each time we add one more parameter that we have to learn, and each time adding a little bit more flexibility in the shape of the curve that we learn. Okay, those are parametric models. Now there's another kind of machine learning, and it's the kind that I like and use a lot, which is called data-driven. And here is an example of how it might work. So let's say we have a query. Oh, and by the way, before I delve into this, let me explain a little bit more about how we use this model. Suppose we have created this model, this polynomial model, and we want to know, okay, the pressure has gone down 0.5 millibars, or whatever the correct unit is. So it's gone down 0.5 millibars. How much do we predict it'll rain? Well, we just plug that into x here and x here, and the answer we would get is this value here. So that's how we query a polynomial model. So at any point in time, we can look at the barometric pressure change and ask the model how much does it think it's going to rain. And it does pretty well, except when we start getting here, to significant negative changes, it'll predict more rain than is likely to actually happen. Okay, that's a query for a parametric model. Let's now look at a query for a data-driven model. At this same point, at barometric pressure has gone down, 0.5. So this dotted blue line represents the location of that query. Here's how the data-driven model works. It says, okay, which points are in our historical data are close to where this query is. So that's these left and right lines sort of represent the area that we're going to collect the data from. And then we can do something as simple as just take the mean of all those points and the mean value, the y mean value, and say that's our forecast. Now if we look at queries across the whole span of the data, I've drawn this blue line to represent what the model would end up looking like. Notice that it fits the data very nicely everywhere. Now this is a made-up example, but this is typical, typical kind of thing you'd see. It can follow all the little twists and turns of where the data takes us, and very naturally and easily, and it's driven just by the data. And we don't impose a model, a parametric model on top of that. So if we compare these approaches, there's pros and cons to each approach. Let me step through those really quick. Parametric model pros are that they don't overfit, usually anyways, which means that they tend to create a smooth line that doesn't zig and zag with each little piece of data, and they generalize fairly well. They're very, very fast at runtime. You just have these, 3 parameters. You do a quick calculation, and boom, you get the prediction. A problem with them is, of course, nonlinear data or non-polynomial data. Parametric models aren't able to fit those very well, and sometimes, to some extent, they sort of oversimplify. Now, if we look at data-driven, pros for data-driven is they can model fairly complex data very well. Another nice thing about data-driven is it's easy to add data and remove data. So, for instance, these dots might represent the most recent few months of barometric pressure and rain data, and if we want to drop off the older data and add new data, it's sort of a trivial thing to do with data-driven models. And you can do it continuously, and you don't have to relearn. You just use the data directly. Some of the cons, at runtime, they're definitely slower than parametric models because you have to consult all the data and find the nearby data values. It requires sorting and distance calculations and so on. So it's slower at runtime. And sometimes data-driven models are definitely more susceptible to overfitting, which means that they model noise in the data perhaps more than actually the underlying principle. So that early example was a one-dimensional example. Remember, barometric pressure is kind of the x. So the input is one dimension, barometric pressure, and then y being how much rain. We can extend this approach to multiple dimensions fairly easily. Here again, a made-up example. We have 2 components now of our x. One is the barometric pressure, just like before, but the other is humidity. So again, I've colored when it rains, I've colored the dots green. You can kind of imagine that these values are now sort of coming at you out of the screen, that y is sort of the 3rd dimension. So a red dot means there was no rain, so it's low, and green dot means there was rain, so it's a high value. And as you can see, again, made up data, but over in this corner where the barometric pressure has dropped a lot and it's humid, we're likely to see rain. But even if the barometric pressure goes down and there's not much humidity, we might not see rain. So that's the reason for these dots being colored red here. Now we can, instead of the query now being just a like an x, single x, it's a 2-dimensional x. So we measure the humidity and the pressure change. So a query in this sense is a particular barometric pressure and a particular humidity value. And we can query the same way. We look at the nearby values and take their mean, and that's our result, is the mean of those nearby values. Now this approach that I've been showing you, this data-driven approach, is, and of course parametric models are data-driven as well, but the idea being that you're sort of keeping the data around and not reducing the size as you do in parametric models. Anyways, an advantage of this, the approach that I've been describing is called k nearest neighbor, where we look for some number of nearby values. Presumably those are the ones that are most similar to our query and are most predictive of what's going to happen. And we take that mean, and that's the result of that is k nearest neighbor. Okay, so we can apply this to the markets as well. So instead of weather, we can think about stocks, and instead of, say, barometric pressure, we might use factors of stocks like PE ratio, news, and instead of estimating rainfall, we might estimate future price. So that's a way that we map from these examples I've been showing you to a stock market example. Now there's lots, this is just a taste of what we can do here. Here's one example. Each dot here represents the one stock in the S&P 500, and we've plotted them in a three-dimensional space. So we went from 2 dimensions there, of barometric pressure and humidity. Now we're using 3 dimensions, and we're using technical indicators to place each dot in this space, and we've colored them according to their future return. So you can see some patterns here, like over in up in this corner, we tend to have reduction in future price. Blue is low price, whereas the further we get out this way, the sort of warmer the color, and actually the more it went up in the future. So we can apply these same principles to this kind of data to estimate future prices. Now there's like I said, this is just sort of a taste of what machine learning is about, and there's lots of questions to answer. These are a few of those questions. Which features should you use? You can use machine learning to find those features as well, or you can use human insight. Which data should you use for the models? So suppose you know which features you ought to use. Well, which group of data, how far back in history should you go? Should you go back just 1 month, or should you go back years? How do you assess if the model is good? Well, clearly by its predictive value, but there's lots of different ways you can measure the predictive value. And a big challenge is avoiding overfitting. And these are all the topics that we'll discuss in more detail as we get into machine learning. Thanks for your attention, and see you again soon. Bye-bye.